All right, I'm going to get started now. So today's talk will be about genuine G-spectra, which I think for a lot of people maybe is something that you already know about, but I want to explain why genuine G-spectra are important for this story. I want to begin first with some things from last week. So just to review a couple things and also clarify a couple points that I made. So we last week looked at these higher real K theories and looked at some finite subgroups of the Morava stabilizer group. And in particular, we observed that when you look at the automorphism group of a height H formal group law, that you can recover this as the valuation 0 elements in the F in the endomorphism ring of the formal group law, and that's the same thing as the valuation 0 elements in the localization of that at P, because this endomorphism ring turns out to be some kind of non-commutative DVR. And then this thing, which is what we called DH last week, was this element of rank H squared in the Brouwer group of QP. Okay, and then we used some field theory to extract some finite subgroups of this. So in particular, we showed that when the height H is of this form, that there is a cyclotomic subfield of this DH. So in particular, we were able to extract a primitive p to the nth root of unity in this DH. And then we used this norm formula to calculate its valuation. And so we checked that its valuation was 0, and that the valuation of it minus 1 is 1 in this case. And that tells us that in particular, this tells us that the element is in the Morava stabilizer group. So we had a CP to the n subgroup. And it also tells us a bit about what the power series corresponding to it looks like. So this told us we have some element in the Morava stabilizer group that looks like this, where T1 is non-zero. And that's like kind of the crucial point to make the whole thing work, because we observed that, okay, let's take the prime to be 2 now, that when we look at the classes in the Adams-Novikov spectral sequence that lift Hn squared, we saw that there was a certain lift of it called beta 2 to the n minus 1 over 2 to the n minus 1. This lifts Hn squared, and it admits sort of nice cobar representative. So namely, it looks like T1 to this power tensor itself in the cobar complex mod the ideal I, 2v1, v2, and so on. So mod something in the kernel of the map to the atom spectral sequence. Okay, and so these facts together told us that, well, we could detect this element by looking at the subgroup of the Morava stabilizer generated by this primitive p to the nth root of unity. So in particular, you can turn these facts into a calculation that tells you that this element has non-zero image in the Cp to the n group cohomology of the coefficients of Morava E theory at that height. Okay, so that's how we proved the detection theorem. And I just want to have some of this in the background for us today. And remember that we proved a more general version of the detection theorem than what is in HHR. Namely, we showed that this beta class always has non-zero image on X when you look along this map, the map induced on X by this, and in particular that also when you take the height here to be greater than 2, that the kernel of that map on X is the same as the kernel of the map to the atom spectral sequence. And that was also something we needed for the detection theorem, which told us in particular that the sort of minimal case to look at was n equals 3, so C8 and height 4. Okay, that's kind of the story from last week. Are there any questions on that? Okay, cool. And then just a couple other points I wanted to say something about from last week is, well, I made this comment that this Morava stabilizer group has finite virtual cohomological dimension. And then that tells you that somehow higher filtration elements should be determined by finite subgroups. And well, and I think Kaif made the comment that it seems like that's actually saying that finite quotients are the things determining the higher filtrations. And that's sort of also true, but there's a general theory of good resolutions of the trivial module over groups that have finite virtual cohomological dimension, which sort of makes the thing I said also true in some cases. And I just, all I want to say is that you can read more about this in the work of Hans-Werner Henn and this paper, Gors, Henn, Mahowald, Resk, where they actually carry that out somewhat explicitly in the height 2 case. And in particular, there's a survey of Hans-Werner Henn called a mini-course on the Morava stabilizer group or something like that, where he discusses this, which clarifies that point a bit. Okay, and just one last thing from last week I want to review. So I stated this unpublished theorem of Hill, Hopkins, Ravenel that describes how the homotopy groups of Morava E theory look as a G module when G is a finite group. And in particular, in the case where you have a cyclic P group, it looks like the symmetric algebra on induced reduced regular representation sphere with the class inverted and completed at an ideal. And the first thing I want to say about that is, well, let me just now state it more explicitly at the prime 2, which is what we're going to use. And also I can give you a reference, namely the general theorem is an unpublished theorem of Hill, Hopkins, Ravenel, but the prime 2 case appears in a paper of Baudry, Hill, Shi, Zheng called Models of Lubin Tate Theory, something like that. And yeah, they prove the prime 2 version of the statement in some form. And just to unravel this a bit, I mean, when I take the prime P to be 2, then this rho bar is just the sign representation. So what this is saying is that equivariantly, this is just the norm from C2 to the n of a polynomial ring, again, class inverted and then completed at an ideal, where the generator U generates a sign representation. Okay, so this was, first of all, interpreting this composition sim of ind as this norm construction, and then interpreting what the symmetric algebra on a sign representation is. Okay, and the big upshot of that is that, well, if you wanted to prove this equivalence, then the adjoint property of the norm tells you that all you have to do is write down a C2 equivariant map. So this equivalence sort of comes from writing down a C2 equivariant map like this. Sorry, so maybe let me get the numbers right, so I write something correct here. This should be pi star e 2 to the n minus 1. That's the one that has the C2 to the n subgroup. And yeah, and you can prove this just by writing down a C2 equivariant map and norming it up. And we're going to sort of mirror that construction on the spectral level. So I wanted to review it again. Okay, that's all I want to say about last week. So now I want to move into connective models and start talking about genuine G-spectra a bit. And what I hope to do today is just give some sense of why genuine G-spectra play a role in this story, because so far as I've told it, they haven't appeared. We sort of proved this detection theorem and reduced everything to understanding the homotopy fixed points spectral sequence of C8 acting on Morava E theory E4. And that's, of course, a Borel equivariant thing completely. And really the role of genuine G-spectra is to take this computation and replace it with one that can really more easily be done. And just as a kind of like historical note, my understanding of the story is that they really did try to just compute this. And they did something like compute the sort of n, one smaller value of n, like the n equals 2 case of this, so that'd be a C4 action on Morava E2, and this took them like 100 pages to write up correctly, and they had the sense that they could maybe do this computation, but that maybe it wouldn't really be believed by anybody. And well, the reason that was kind of the case is because, well, there are a couple things that are really hard about this computation. So first of all, you're working with this Morava E theory, so you have power series rings which are not finitely generated and sort of hard to work with, don't have any good finiteness properties. And then the spectral sequence themselves had no good vanishing regions. Okay, and I want to elaborate on mostly the second point for a moment, just by returning to this example of the C2 case of C2 acting on K theory. So let me on this side just remind you what the homotopy fixed point spectral sequence for Ku with the C2 complex conjugation action looks like. So on the 0 line, you have class 1, v1 squared, v1 to the minus 2, and then you have these eta towers. Okay, and so it's sort of upper half plane, but it doesn't really have any other good vanishing regions. I mean, there's no vanishing line of any kind, and well, that makes it somewhat tricky to deduce the differential that we talked about last week, namely this D3 here. Okay, so I outlined a method last week, but that is a little bit tricky. And well, you could compare this to an easier calculation where you look at the Adams-Novikov spectral sequence of connective real K theory, KO. Okay, and I'll just tell you what this looks like. So first of all, it's first quadrant spectral sequence. And it has a vanishing line of y equals x. So everything's concentrated on or below the line y equals x. And yeah, and the point is that, well, as a ring, this is like z adjoined v1 squared and eta, mod 2 eta. This is just that with v1 squared inverted. And in both cases, since you just have two algebra generators, and eta is a permanent cycle, then the spectral sequence either supports a differential on v1 squared, or has no differentials. But on the right-hand side, there are infinitely many possibilities of a differential this could support, because you have all these eta towers coming in forever and ever. But in this case, there is only one differential that this could possibly support, namely that D3, because of the vanishing line. And so then you can make some arguments which are perhaps easier. So if you know, for example, that the homotopy groups of this are 8 periodic, then it can't be the case that the spectral sequence collapses on the E2 page, and so there has to be a differential, and there's only one possibility. So just an example of, how something like a vanishing line can simplify a calculation. And this is the sort of thing that they were hoping for that you don't have in this C8 homotopy fixed point spectral sequence. So let me give another example, which is harder to illustrate, but is a somehow better example, which is the homotopy fixed point spectral sequence converging to the homotopy groups of TMF, at least K2 locally. So here is some big subgroup in the height 2 Morava stabilizer group. And this spectral sequence is really crazy. I mean, it's just has classes everywhere. There's no good vanishing. And yeah, there are many differentials in it, so you can't just sort of, come up with some argument for this D3 and be done like you could in that case. Here there's really a lot of things to do. And some of this sort of connective models perspective really came from this example when Hopkins Mahal noticed that if you could build this connective version of TMF and look at its Adams-Nabokov spectral sequence, it would also have this y equals x vanishing line, and well, it would be much more computable. And that is, what they did, and is a sort of important part of this whole TMF story. Okay, so that's sort of a prototype of this, and so let me say now what a connective model is. So we're trying to understand these higher real K theories. These are fixed points of Morava E theory at some finite subgroup. And this is something which has some uniform definition. And a connective model is something that doesn't have a uniform definition, but just something that you hope to exist that resembles, this connective TMF or this connective KO in some sense. And some things you might ask from this are that, well, that this little EON, this connective model, is connective, and that it should be an FP spectrum in the sense of Mahal-Waldresk. So this means that its cohomology is a finitely presented module over the Steenrod algebra and is a good sort of finiteness condition that you can ask on a spectrum, and has, both of these examples have this property. And you should ask that, this sort of sees the same height n information as this does. So you should ask that this map is a K and local equivalence. Okay, so you probably could and should ask for more, but this is sort of the bare minimum. And again, your examples you should have in mind are the map from KO to KO and the map from TMF to TMF. Those are really the prototypes. Okay, and the idea that HHR had was, constructing this TMF is like really specific to this spectral algebraic geometry definition of TMF, and at some arbitrary height where you don't have some algebra geometric input, it's not clear you could mimic that construction. So they tried to do something equivariant, and so what they tried to do, let's just keep it in the context of the example we care most about, is say, look at this E4 and try to construct a connective model of it before passing to fixed points. So a sort of connective model of the big E4, but C8 equivariantly. So if I could construct this C8 map, then what I could do then is apply the genuine fixed points functor to this. And this might give me a candidate for this connective model. Okay, so I'll say more about this genuine fixed points functor. That's what today's talk is about, and why I chose that one as opposed to homotopy fixed points or something else. But maybe the first thing to say is that when you take homotopy fixed points, you almost never get something connective. And so that's sort of the first reason why taking homotopy fixed points over here is not going to be the right thing. But the sort of goal they had in constructing this was to say, okay, let me look at the top row now, is that the homotopy groups of this equivariantly looked like this sim on the Dieudonné module with some junk on it. And they hoped to basically construct just the sim m part. Okay, and then they, in order to define this map into pi star en from sim m, they needed the norm to do that, and so then they tried to mimic that on the spectral level. Okay, and so our goal is, is to construct this E4 equivariantly so that it implements this sim m. Okay, and let me just say, before you even know anything about this E4, like whether it corresponds to this sim m or not, you do already know that when you construct a map like this, well, as long as it's a map that factors over the sphere, that this little EO4 satisfies the detection theorem. All right, so the detection theorem we proved said that if the Kervaire class survives, then it's non-zero in here, and so of course it has to also be, then it's non-zero in here, and so then it also has to be non-zero in there because this map is unital. Okay, so that means we can sort of use the detection theorem here, but work entirely over here in some spectral sequence we construct to compute that. Okay, and the prototype for this equivariant construction of a connective model is this Atiyah connective real K theory. And the basic thing I want to think about, the basic thing that I want you to think about with this example is that, well, I can start off with mu, and as a quotient of it, I can construct ku. Okay, so at the prime 2, this ku is a BP1, and what some work of Hugh-Kriess showed is that I can equip this whole diagram with C2 actions by complex conjugation so that I get these sort of real versions of this. And then when I pass to genuine C2 fixed points, I get KO. So that was one of our prototypes of the connective models, and this is the sort of equivariant construction of KO that I'd like to mimic, is that I can start with something like mu and build my sort of sim m thing as a quotient of mu, equivariantly. And of course, we know that pi star ku equivariantly is this sim on a sign representation. Okay, so that really starts to match up with this stuff appearing up here. Okay, cool. Let me now move into genuine G-spectra. So everything I said up until now is kind of motivation for why genuine G-spectra are appearing, and now I want to step back and just sort of give the basic definitions of these things. Okay, so first I want to start with Borel G-spectra and hopefully give some explanation on why genuine G-spectra are some kind of improvement of that. So Borel G-spectra are just spectra with G actions. So this category. And there are many, many ways of thinking about genuine G-spectra, but I want to focus on one just for the start today that I think plugs well into this picture, which is that genuine G-spectra are a decompletion of Borel via geometric fixed points. Okay, so I say that this fits well into this picture here because we are indeed sort of trying to decomplete this pi star En, and that is sort of what genuine G-spectra will do for us in this story. And there are many ways of thinking about the sense in which this is a decompletion, and I want to now state a few of those. So the first thing that I want to say about that is just that there's the following adjunction between genuine and Borel. So I'm going to say a lot of things about genuine G-spectra before I define them to sort of motivate the definition. So I haven't defined it yet, but this is going to be the category of genuine G-spectra. And there's a forgetful functor here to Borel G-spectra, and its right adjoint is denoted like this often. And this turns out to be a Gauss field localization, actually at the suspension spectrum of G, so the suspension spectrum of the G space G. Okay, and that is sort of already a sense in which it's a decompletion. This category sort of completes to this category in the sense of Gauss field localization. And the Gauss field localization that it's doing, you can think of that in the following way. Well, there's a forgetful functor from Borel G-spectra to spectra, which is conservative because that's a functor category. And this is exactly the localization at that. So this is the functor which inverts maps that are equivalences on underlying spectra. So I want to name this composite phi E, and that's what I mean by taking the underlying spectrum. Okay, so that's like the first sense in which it's a decompletion, and then I want to give more and more ways of thinking about that. So maybe the next one, which is much stronger, would be the Siegel conjecture, which is a theorem, Carlson. And it says the following. So I can look at the pi 0 of the sphere in genuine G-spectra, which is what I mean by this, and look at the map induced by this phi E to pi 0 of the ordinary sphere. And this turns out to be the augmentation map of the Burnside ring for the group G. So let me say, because I don't think I did yet, that everywhere G will just be a finite group. Okay, and what the Siegel conjecture says is that if I look at the augmentation ideal, so the kernel of this map, then the map from the sphere to its Borel completion, so it would be like the unit of this adjunction, is the completion of the sphere at the ideal I. Okay, so that's one form of the Siegel conjecture, and if I look at this on pi 0, it's saying that I can compute the co-homotopy of BG as the completion of the Burnside ring at this augmentation ideal. Okay. So again, we see this sort of completion idea that I sort of get from the genuine to the Borel thing by completing at something. That ideal is not the same one as this ideal, but okay. Great. So now I want to bring in the geometric fixed points part of this. So I said it was a decompletion via geometric fixed points, and so I want to now bring in, well, the Tate square. Other questions I raise? Everybody already knows everything about genuine G-spectra, so it's kind of just like fan fiction, you know. But I think we.
I can ask a question about not genuine. Why in this connected model stuff?
Yeah. I mean, okay, yeah. I mean, so you could maybe just start by asking for it to be like connective and that the homotopy groups are finitely generated and something like that. But I think it's well, okay. I think one thing you could say is that it tells you that the atom spectral sequence should be interesting, should be computable, and I think in the height 1 and 2 story, you know, using these KO and TMFs as an example, that's sort of one of the things that makes them the most useful, is having this computable atom spectral sequence. Let's see. I mean, there are other things that, you know, this category of FP spectra is like a small category you can apply K-theory to, and there are ways of understanding things about finite spectra in terms of FP spectra from that K-theoretic point of view. So I think, I don't know, maybe the better answer would just be to say that it guarantees that it's connected with finite spectra in a more intimate way, because FP spectra have this property that you tensor with the finite spectra and you get something pi finite. So that's, yeah, I mean, I think that knowing that you have this as an FP spectrum shouldn't a priori tell you, you know, that the Adams-Novikov spectral sequence of this is going to be a huge improvement on the homotopy fixed point spectral sequence of this. But yeah, I think there are other things people will want from these connective models beyond just that. Okay, so now let me get into the Tate square. Okay, so I want to say a bunch of things about genuine G-spectra, but just write things about genuine CP spectra for P a finite group, because this makes things much more concrete. So I will say things about CP spectra, but they all have analogs for any finite group. Okay, so I want to give the following sort of proposition / definition of genuine CP spectra. So this category can be written as the following pullback. Okay, so here I have this category of Borel CP spectra, and this is the Tate construction. So let me first say the sense in which this is a definition. So this Tate construction is something that can be defined purely in terms of Borel data. If you regard this as a proposition, then I can tell you that the Tate construction is something, you know, that as defined by Green-Lees-May is something that you can see easily in the genuine category. But if I want to use this as a definition of this, then I need a Borel definition, and that comes from this construction of Hopkins-Lurie of norm maps. So they construct a map for a Borel CP spectrum X, called this norm map, whose cofiber is by definition this Tate construction. And this norm map is supposed to be some spectral version of the map I get for a G module M. It takes an element in the orbits and sums over its orbits. Okay, and that gives me a definition of the Tate construction, which which defines these functors and gives a definition of CP spectra. On the other hand, if I think of this as a proposition, well, this comes from the following pullback squares one has for a genuine G spectrum X. So, well, when I, sorry, let me say this, let me say the following first before I get into the proposition side of this. On the definition side, if I take this as a definition of CP spectra, then it defines this genuine fixed points functor as the following pullback, where the geometric fixed points functor is the evaluation at 0 here. Okay, and that defines the genuine fixed points functor. On the other hand, if I want to regard this as a proposition, then it comes from these squares, which are pullback squares in CP spectra, which in turn come from, say it like this, the following cofiber sequences. So I can take the space ECP and take the collapse map to a point and call its cofiber E tilde CP. This gives me a cofiber sequence of G spaces. And the fact that this smash this is contractible tells you that this gives you a smashing localization in G spectra, and you get this pullback square out of it. So to be more precise about that, let me maybe just fit this in here. Yeah. Okay, so this cofiber sequence for a CP spectrum X induces the following diagram of cofiber sequences. And it's easy to check that this map here is an equivalence, which tells me that this square here is a pullback square. And I obtain this pullback square from this one by applying to the genuine fixed points functor. Okay, and the point is that, well, if I take genuine CP spectra as given, and I give myself this cofiber sequence, then this Hopkins-Lurie norm map is actually just coming from this map down here, applying genuine fixed points to that map. Okay, I will now say some more things about these Tate squares, but I just want to bring these in to introduce the geometric fixed points functor. So I said it's some kind of decompletion via this functor. And well, the sort of thing that makes it a good decompletion is that this functor has good properties. And those properties in turn come from the relationship between genuine G spectra and genuine G spaces. So now I want to say some things about G spaces. So Borel G spaces is, again, this functor category. And the category of genuine G spaces is the following, also functor category, where this O op G is the full subcategory category of finite G sets on the orbits. Okay, so for example, if I take my group to be CP again, then a genuine CP space is a diagram like this. So this comes from evaluating this functor at the orbit G mod E. This is at G mod G. And the point of this is that in the Borel category, you only have the homotopy type of the underlying space carried along. And this genuine category forces you to have the homotopy type of the fixed point space also be a part of your data. So for example, this cofiber sequence is uninteresting in the Borel perspective because the underlying space of this E tilde space is contractible. And so in the Borel category, this is contractible. But it's not in this genuine G spaces category because we remember the fixed point space. Okay, so that's genuine G spaces. And now I want to state some properties of this geometric fixed points functor, which, as I said, depending on whether you take this as a proposition or a definition, we already defined. Okay, so this is a functor from CP spectra to spectra, and it has the following properties. So first, it's a symmetric monoidal left adjoint. Second, it satisfies the property that on suspension spectra, it gives me the fixed point space. So X is some G space, a genuine G space. And these two functors together are jointly conservative. This is the underlying spectrum functor. This is the geometric fixed points. And then finally, we have that if I take the geometric fixed points of a Borel complete CP spectrum, then I get the Tate construction. Okay, and this is something I want to emphasize, I'll say more about, which can be thought of as the Adams isomorphism. Okay, and the reason I want to point that out especially is because, well, we want to build this category of genuine G spectra out of G spaces, and we want it to be somehow the right stable category. And the more obvious choice would be this category of naive G spectra, which would be the stabilization of genuine G spaces. And that's a category you can consider. You can define a sort of genuine fixed points functor in there, which again is going to be evaluation at the CP mod CP orbit. And you can define your geometric fixed points in the same way we did it over there. You take this cofiber sequence and then apply genuine fixed points to it. And that functor will satisfy all the properties except 4. So this doesn't satisfy 4. It doesn't satisfy the Adams isomorphism. And what that tells you is that it doesn't have some nice relationship to the Tate construction. And so from the point of view of like these homotopy fixed point spectral sequences, we would like to be able to do genuine calculations in terms of this square. And we like to be able to compute this with the homotopy fixed point spectral sequence and this with the Tate spectral sequence. And the Tate spectral sequence is some spectral sequence which relates homotopy groups to Tate cohomology. And if you looked at that square in this category, you wouldn't have that. It just wouldn't be the same thing as the Tate construction as defined by Hopkins-Lurie, for example, and it wouldn't be clear how to compute it in terms of some familiar algebraic invariant like Tate cohomology. Okay, so the Adams isomorphism is really, really crucial. And let me just state in another form what the Adams isomorphism says. It gives you this sort of surprising looking equivalence between a fixed points functor and sorry, that should be homotopy orbits, and the homotopy orbits functor for X, a G spectrum. Okay. Yeah, and the point for now is just that it somehow gives us this connection to the Tate construction. Okay. Okay, actually, I think I will take the pause there and talk about the norm.